So for the remainder of today's class, like to take a bit of a laid-back approach to an introduction to determinants. Today we're going to talk about the determinant of a 2x2 matrix, which means that there's not going to be a lot for us to talk about in terms of computation, in other words, the how of taking a determinant, because that's pretty quick. What I'm more interested in talking about today in our introduction to determinants is why. So what does a determinant actually mean? What does it tell you about a matrix, about the linear transformation that matrix represents? So that'll be the goal today, is to talk about 2x2 determinants, how to compute them, and then how to figure out what they're telling you. Tomorrow we'll push forward and talk about the 3x3 case and larger for square matrices, and then some of the applications of determinants, including how to compute them, first of all, in a variety of different ways. Cofactor expansion being the particular new method that we'll talk about tomorrow, and then also a few words about using determinants to compute something called the adjugate of a matrix, which is very much like the inverse. It's very similar to the inverse of a matrix. So what we're going to find out ultimately is that we're going to have today an interpretation of the determinant of a matrix which is very geometric. It'll give us a very nice picture, but we'll also see over the course of tomorrow and then maybe Wednesday if we need to, that the determinant can actually also help us to solve square systems, to solve AX equals B, when A is a square matrix, when A has as many rows as it has columns. So A is n by n. So that's going to be the second part of the story, is that there's this nice algebraic interpretation of it as well. But for today, we'll focus on the geometric and try to uncover what the determinant is as well as some of its properties by thinking about what it tells us about a 2x2 linear transformation. So first of all, let me dial in a new linear transformation here. Maybe, I don't know, I'll just sort of play around with these a little bit. Maybe stretch this out to the side some more. Whoops. This thing is jumping around on me today. Alright, there we go. So here's a matrix, 1, 1, 1, 4. So first of all, tell me, how do I find the determinant of a 2x2 matrix? Alright, so I multiply on the diagonal, first of all, so I get 1 times 4. Determinant of A, which is sometimes also written as A with absolute value symbols around it. We're going to treat those as being interchangeable. And the first product is the product on the diagonal, 1 times 4. And then I need the product off the diagonal, 1 times 1. And what do I do with those two products? Subtract the 2. So in our example, that's 4 minus 1, that's 3. And I've added this little thing to our app here. We can show us the determinant over here on the right in real time. So I usually think of it as being kind of this little bow tie shape where I multiply in one direction, and then I subtract the product coming in the other direction. So in general, if our matrix is A, B, C, D, then how would we write the determinant of this matrix? AD minus BC. And we've seen that quantity before. We saw this quantity last week, last Thursday or Friday, or Wednesday or Thursday, I guess. We saw this quantity when we were inverting a matrix, a 2x2 matrix, namely. This was part of our shortcut formula. So that's kind of a hint to how we're going to end up being able to use determinants to compute the inverse of a matrix. So even though we won't talk about this in detail today, I think the comparison is useful to see right now, that the inverse of the matrix, ABCD, what was the 2x2 shortcut?
U1 divided by AD minus BC.
So you divided by the determinant.
And then you multiplied by the matrix D negative B negative C A.
Great. So that was the shortcut for inverting a 2 by 2 matrix. And suspiciously, the determinant is sitting out in front, determinant of A. But then, as a foreshadowing to what we're going to talk about tomorrow, it turns out that this matrix over here, which in the 2 by 2 case was the same as just sort of flipping some entries around, then maybe changing the signs on some other entries. In the higher dimensional cases, there'll be a little bit more to do here. But this matrix is what we call the adjugate of A. And there's a word that you don't hear pretty much anywhere outside of mathematics, as far as I know. Although, I feel like in the legal system, adjugate means something else. That's adjugate general. Or maybe I'm thinking of adjutant general. Anyway, it's a weird word. And this is the only place that we're going to see it. But that's the role that's being played by the second matrix here. So in general, when we talk about adjugate tomorrow, that's going to be the role that it plays. That the inverse of any matrix we can find just by dividing 1 over the determinant of A multiplied by the adjugate of A, which I'll also write A dj. So it's going to give us a new way to find the inverse of a matrix. Instead of row reducing with the identity on one side until we get the identity on the other side. Instead, we'll just be able to compute a determinant, which is not that bad, and then an adjugate, which turns out to be a lot of work. The only reason the adjugate is a lot of work is that every entry of the adjugate is a determinant in and of itself. So if I'm doing a 3 by 3 matrix and if I'm computing the inverse this way, I end up needing to compute 10 different determinants in order to do it. 1 for the factor out in front, and then 9 for the entries in the adjugate. So it's not the most efficient way of finding an inverse, but it does maybe give us a different perspective on that whole process. So that's the algebraic, way that the determinant shows up. But again, I wanted to talk today about what this determinant actually represents. So taking a look at the diagram that we have up here of the linear transformation that's defined by the matrix A. Where do I find this number 3 in this diagram?
The x values.
The x values?
Oh, I'm sorry, where, that wasn't clear enough, but like, where they meet in the top.
Right here?
Yeah, down.
The corner. Okay. So remember, this corner is if the sides of my parallelogram over here are the vectors v, which in this case is 1, 1, and w, which was 1, 4, then this upper corner of this parallelogram is actually just v plus w. But v plus w here would be 2, 5. So the determinant is going to have something to do with this figure over here. But it actually doesn't describe the location of a single point of this parallelogram. Rather, it describes something else. Let's play around with this a little more and see if we can get a better feel for it. So if we just go back to initial settings here, and then let's take this codomain vector. Let me just stretch this out horizontally. Whoops. So that what I get here is so here's another example, 6001, and the determinant is evidently 6. Where do I find the number 6 in this diagram over here on the right? It's the width. In this example, it's the width of that rectangle, which is 6. But why should the determinant pick on the width? What if instead of stretching that rectangle the way that I did, what if I bring that back to the original and instead I decide to do this? Now again, the determinant is still 6, but now the width of this rectangle is no longer 6. Instead, 6 is the height. All right, so what one general idea can we use here from geometry that can encompass both?
Well, it depends on what vector you use to stretch it.
It does. So let's take this and stretch it. In addition to stretching it by a factor of 6 vertically, let's also move it horizontally some. Now my determinant is 24. And the reason my determinant is 24, at least from an algebraic perspective, is that that's what I get taking the product on the diagonal. If I'm taking the product on the diagonal, I'm really taking the product of the width of this rectangle with the length of this rectangle. And so I'm getting the area. So one of the first interpretations for the determinant of a matrix is it's the area of the image of what? So what kind of area did we start with over here in my domain?
Zero. No. 1.
Yeah, 1. We started over here with a unit square, right, which is 1 in width and 1 in height. So the area began as 1. And then under this linear transformation, the area turned into 24, which was the determinant of A. So of course then I have to ask, what happens if I start in the domain with a different amount of area? Let's say instead of mapping 1, 0 onto 4, 0, and instead of mapping 0, 1 onto 0, 6, let's suppose that I instead, let's screw around with these vectors back in the domain. So that maybe I'll have 0, 2 here, and just for fun, maybe 3, 0 over here. Who knows?
What if you don't have a 0 here?
What indeed? Yeah, we'll talk about that in a moment here. So let's talk about the determinant of this matrix now, this linear transformation. So now instead of starting with something whose area is equal to 1 in the domain, now I'm starting with something whose area is 6. It's 3 by 2. But then the area of its image over here is still the same. This is still a 4 by 6 rectangle, so it's 24. But what's the determinant of my matrix now that represents this linear transformation? Now my determinant's equal to 4. So what's changed? Or maybe how can we, in light of this information, what is a more general way to interpret what the determinant tells you about a linear transformation?
Domain times the matrix gives you the coordinate.
Yeah. So the determinant of A tells you how much to multiply an amount of area in the domain by in order to get the area of its image sitting in the codomain. So let's try and write that down here. That the area of an object in the codomain, a two-dimensional region in the codomain, is equal to the product of the area in the domain times the determinant of A. That would seem to work here. So we start out with a rectangle whose area is 6, and we end up with a rectangle whose area is 24. So the determinant is, I like to call it the area factor, equal to 4. So a couple of questions. So just bumping the image vector over here up even slightly ends up achieving a vertical shear of this vector. But notably, the interpretation of the determinant, even though we no longer have a rectangle going to a rectangle, the interpretation is still the same. I started out with something whose area is 6 over here, and then I have this matrix whose determinant is equal to 3. And so based on that information, what do we predict that the area of this parallelogram over here now is going to be? 18. The 6, which is the image in the domain, times the determinant, which gives me an area factor of 3, multiply 6 and 3. Gives me the area in the codomain. So the good news is it doesn't matter if we start with a rectangle and end up a rectangle, or if we start with a rectangle and end up a parallelogram in more generality, or start with a parallelogram and end up a parallelogram, which is what the only thing linear transformations are allowed to do, with one exception. What happens if I take these vectors and arrange them in just such a way that let me tweak that a little so we can see it better. So let's make that there we go. then likewise there. So let's make it so that I'm sending 3, 0 and 0, 2 to the same place, namely 4, 3. So again, I'm starting on the left-hand side with a rectangle whose area is 6. But now in this picture, I'm ending up with a figure on the right-hand side whose area is what?
0.
It's 0. And so the determinant, as we expect, based on this picture, the determinant 4/3 times 3/2 is 4/2, minus 2 times 1. So the determinant is 0. So now tell me as much as we can say about the matrix A and the linear transformation that it represents. How many solutions? Yeah. How many solutions to the equation AX equals 4, 3? Well, there's at least 2, right? Namely 3, 0 and 0, 2. But because there's at least 2, there have to be how many? Infinitely many. Right, we can't have 2 solutions in linear algebra without having infinitely many solutions. Thus, infinitely many. And so since there's infinitely many solutions, what can we say about the, well, let's say, what can we say about the number of free variables in A? Does it have any free variables? Yes. So there has to be at least one free variable. So what does that mean about the invertibility of A? Is A invertible or is A not invertible? Remember what our criteria were? A is not invertible. Why is A not invertible?
Because when you take the, to be invertible, you have to have the inverse. And you won't be able to take the inverse.
Right, because there's a free variable, that means that there's a column that doesn't have a pivot. There's a column of A that's not a pivot column, which means that I can't row reduce A into the identity matrix. Can't find A inverse, at least one non-pivot column. And all of that from this. All of that just from the observation that the determinant of this matrix was 0. And again, to think about it from an invertibility perspective, if we try to go backwards, we would not know where to send a point like 4, 3, because it would have to go both to 3, 0 and to 0, 2, as well as infinitely many other places along the line that joins those 2 points. So the solution set would look something like this. So we can't go backwards. And thinking about it geometrically, that's because we have taken an entire rectangle's worth of area over here in my domain, and I've collapsed it down into something which doesn't have any area in the codomain. And so because I've completely collapsed a dimension going forward, I can't uncollapse a dimension by coming backward. It's kind of a geometric perspective on that.